Mark P. Otten back with you.
Okay, so this is your follow-up to your two-way ANOVA video, just talking about effect size for all of these strange combinations of tests that we run with main effects and interactions and whatnot. So going back to our independent samples example, that was the first one, that was the jumping jacks example from your video. Not all two-way ANOVAs are done by way of jumping jacks examples, just this particular one. But anyway, that would be a strange rule to have in your statistics book. So I just happened to choose the jumping jacks example for you guys since it's silly and you might remember it. Okay, so when you do a two-way ANOVA, you're going to have a main effect result for the first IV, main effect result for the second IV, and an interaction. 3 results, and thus 3 effect sizes. And so you're going to calculate each one in turn. When we did a one-way ANOVA, you see eta squared there. It was your sum of squares between divided by your sum of squares total. We're going to take this same formula and kind of adapt it for when you have more than one IV. So the adaptation is the partial eta squared. And basically what happens is you have 2 IVs plus an interaction, 2 main effects plus an interaction. And so when you calculate that original eta squared value, it's sort of lower than it should be. It doesn't get, like a higher effect size is a good thing, and it doesn't quite give your effects enough credit by just calculating a eta squared. So you edit the denominator in this case to make it a little bit smaller, the denominator that is, making the entire fraction bigger. You don't need to know necessarily the logic of this. I'm just giving you a little bit of background as to why there's the change here. So before it was sum of squares between divided by sum of squares total. Now it's sum of squares effect on top. That's actually sum of squares between. It's just I'm calling it effect because there's 3 effects here. There's the main effect for one IV, there's the main effect for the other IV, and the interaction. So for example, for the first main effect, sum of squares between is the sum of squares between for that effect, that main effect. And then that changes. Suppose you're doing the interaction, the sum of squares effect is the sum of squares between for the interaction. We just, to simplify that a little bit, you call it the sum of squares for effect, whatever effect you're on. And then that's the sum of squares between for that effect, technically. And then the bottom part, instead of sum of squares total, is just a little bit reduced, like I said. So you take your sum of squares for effect, that's the top and bottom there, and then you add on the bottom sum of squares error. Okay, so let me show you where all of these numbers come from in SPSS. This is your output for the jumping jacks example. If you're wondering where I got this output, how it came to be, it's in the two-way ANOVA video, so you can refer to that, refer back to that. Your sum of squares effect for the participant gender main effect is your 300. That's right here. That's your participant gender sum of squares. And so if we're calculating an effect size for that particular main effect, we take the 300, we put that on top and bottom, and then we take the sum of squares error, which is 202, which is down here in the error row. And those are the only 2 numbers you need. You just need to place them in the right location there in the formula, and you get 0.598. And then if you go on to the next slide here, the main effect for experimenter gender is exactly the same because the numbers are exactly the same. So the 300 is the one in the experimenter row here. The 202 stays the same. And so you're going to get 0.598 for each of those. Now that's not always going to be true. In this case, the main effects were exactly the same size as each other, but that's not typical. For the interaction here, you see the formula does not change, but this time the numbers do. You've got 75 on the top. That's your 75 sum of squares between for the interaction, or the sum of squares for the effect. That goes on top and also on bottom, and then also that 202 is repeated. So the 202 is still the sum of squares error. That stays the same regardless. And so you get a smaller effect here, 0.271. These numbers max out at 1, and the minimum is 0. So if you're outside of the interval 0 to 1, you know you did something wrong in the calculation for these. So that's for your independent samples, two-way ANOVA. I'm going to talk about the dependent samples and mixed ANOVA effect size values and formulas next. Okay, so just to, I guess, repeat that a little bit, we're going to calculate partial eta squareds then for the other two-way ANOVA examples. The mixed ANOVA example, where we had one IV that was independent samples and one IV that was dependent samples. And that was in your two-way ANOVA video. We ran through the time 1, time 2 IV for, that was your dependent samples IV, and then your independent samples IV was still participant gendered. This is what the output looked like. If you're watching this and you're like, I have no idea what he's talking about right now. Well, just review the two-way ANOVA video, and then you'll still have no idea what I'm talking about. No, hopefully that revives your memory of this example. In the output here, we have tests of within subjects effects, which gave us a lot of our results. That was our time main effect here. 0.409 was our p-value. We concluded that there was no effective time in one's propensity to do jumping jacks. So we can still measure the effect size, however, for that effect, and so we just need to distinguish it from the others. So the sum of squares for effect in this case was 65.33. That's under the time sphericity assumed row, and type 3 sum of squares. We don't really cover types 1 and 2. Type 3 is what you need, and you can just go with that. The sum of squares error is 307.33. That's down here in the bottom. So under error parentheses time, sphericity assumed right here. So with those, you're going to put 65.33 in the top and the bottom. 307.33 goes in the bottom as well, and you're going to be able to calculate your partial eta squared for the time main effect. For the time star participant, that's the interaction effect here. You're going to replace 65.33 in the numerator and denominator with 56.33. That's your sum of squares effect for the interaction. The sum of squares error stays the same, 307.33 for this example, and you can get your interaction partial eta squared. And then finally, for the other main effect, we had to go down here for the tests of between subjects effects. And there you find some new numbers. You find sum of squares effect 736.33. That's in the participant gender main effect row here, 736.33. The sum of squares error is 359.33. And so that's going to go in the bottom. The 736.33 value will go top and bottom. And once you divide, you'll get your partial eta squared for that effect. So that was your mixed ANOVA. Let me do this one more time in case you're really excited to see this one more time. You can see how this goes for the two-way dependent samples ANOVA. Okay, so for our two-way dependent samples ANOVA, everything was contained within this tests of within subjects effects box here. This was our example where we had time 1 and time 2 as one of the IVs, and the other was experimenter gender, presuming that everybody in our experiment had 4 sessions of jumping jacks, thereby wearing them out completely and causing great exhaustion. But anyway, this was how the output came out. For the time main effect, we had 0.359 for our p-value here in the first row, and so the partial eta squared, you might be able to put this together now, would be sum of squares effect 30.08 divided by 30.08 plus 43.167 here in error parentheses time. So that'll give you your sum of your partial eta squared for the time main effect. The process is similar then for the other two effects. So for experimenter gender, the p-value is 0.517 here. Sum of squares effect was 10.08 in the experimenter sphericity assumed row. In the error experimenter row, the sum of squares error 33.167. So you put your 10.083 in top and bottom, 33.167 in the bottom, and divide. And then finally, the interaction sum of squares effect 6.75, sum of squares error 6.5, smaller numbers for this example. And so you proceed from there with those two numbers applied to the fraction.